Hi, my name is Dr. Kyle Koenig.
Hi, my name's Katrina Rodheim.
And we study sleep!
What is EEG? EEG is a non-invasive, safe method for detecting electrical activity in the brain. As sleep scientists, EEG is a valuable tool for us to understand changes in our brain as we transition from being awake to going to sleep. EEG allows us to objectively examine changes in brain activity, eye movements, and muscle activity that we could not see by simply observing.
During an EEG recording, small metal electrodes are placed on the scalp. When placed, electrodes detect fluctuations that are caused by electrical activity of neurons communicating with one another. The tiny electrical currents of many neurons being active in unison can combine to create a big enough fluctuation to be detected through the skull as a difference in electrical potential between electrodes.
Fluctuations detected at electrodes are then amplified, digitized, and displayed on a computer over time. Over time, the fluctuations change, and their changes constitute an EEG recording. You can learn more details about how EEG is collected in general in the video about EEG and event-related potentials in the same textbook resource. Here, we will focus on how we use EEG to study sleep. When we study sleep, we pay attention to large fluctuations of potential over time, which look like waves in the EEG recording. We often call them waveforms or brain waves.
What are EEG waves? The fluctuations that electrodes measure look different over time and in different circumstances. Looking at recordings of EEG brainwaves over time can help us visualize and quantify brain activity as we go about doing different tasks, like sleeping. While studies of event-related potentials, or ERPs, focus on sudden, rapid changes in EEG recordings after specific tasks, sleep researchers are more interested in how EEG brainwaves vary over longer time courses.
Over long time courses, there are many different types of brainwaves, each of which are characterized by differences in their frequency, measured in hertz, and amplitude, measured in microvolts. Using these differences in waveforms, researchers can distinguish between different activities like being awake, quietly resting, going to sleep, or being deep in a dream.
This is what a brain looks like when you're awake. At some points, there are large voltage fluctuations across all of the electrodes, indicating the wearer is moving. At others, we can see large voltage fluctuations in only the electrodes near the eyes, indicating blinking.
And this is what a brain looks like when you're quietly resting. For example, watching TV. As wearers stop moving and begin to close their eyes, voltage fluctuations become less rapid and lower in amplitude.
As these examples show, the appearance of an EEG recording can vary depending on what the person is doing or experiencing. Different mental states, activities, or stimuli can produce distinct patterns in the EEG signal. Sleep is one activity that shows several distinct EEG patterns, and studying these patterns has taught us a lot about what our brain is doing when we sleep.
Here's the first indication of falling asleep. You can see slow rolling eye movements and lower frequency waves. If we jump ahead in the recording, we can see the first physiological indications of light sleep, called K complexes and sleep spindles. If we jump ahead again, we can see the transition to deeper sleep, or slow wave sleep, which is characterized by high amplitude delta waves. And if we jump ahead one last time, we can see REM sleep, or rapid eye movement sleep, which looks a lot like wake, but with these key differences: the absence of muscle tone, and rapid eye movements while the wearer is asleep.
How do we know someone is asleep? EEG can tell us. Beyond that, EEG can objectively capture changes in the brain that we can't see by just observing. We can use this data to understand basic processes like when people sleep and how different phases of sleep affect memory. Though EEG is the gold standard for sleep measurement because of its accuracy, it is a cumbersome, expensive, and often uncomfortable process.
Alternatives, like actigraphy, or new wearable sleep monitoring technologies like Fitbits, can often monitor sleep with less disturbance and for less money. However, they are also less accurate. Altogether, every technique has strengths and limitations, and it's always important to understand the question you're trying to answer, and then to select the proper tools to answer it.